Okay. So, in the last class we are discussing this correlation matrices. We discussed some properties of Hermitian matrices or Hermitian matrices which are also positive definite matrices. Okay. We found out that the eigenvalues of any Hermitian matrix as such, not even positive definite, they are always real, okay, and their eigenvectors are orthogonal to each other. Okay, we have found it out. Then if in addition the matrix is given to be positive definite, then eigenvalues are also positive. If it is non-negative definite, they are non-negative. Okay, this we have seen. Okay, then we are discussing the linear dependence and independence of random variables and all that. So, I just start from there. I continue with the previous discussion on the correlation matrices first. Okay. Do you remember our previous treatment on what is called vector space of random variables, where each random variable was treated as a vector in an abstract vector space of all possible random variables in the world. Okay. And there we defined addition of two random variables as addition of two vectors. What is meant by 0 vector? That is a random variable which always takes 0 values. Okay. Then negative of a random variable means it's again a random variable which takes negative of the original random variable, and likewise it is just in that framework we can discuss what is called linear independence and dependence. Suppose we have got a set S of random variables x1 dot dot xn. Okay. If these random variables are such that none of them can be expressed as a linear combination of the rest or part of the rest, then I can say that this set has no redundancy. Each random variable is independent of the rest. In fact, we call it linearly independent of the rest. Okay. And therefore, on the other hand, if it is that the set is such that at least one vector is expressible in terms of the rest as a linear combination, okay, then it is called a linear dependent set. So, that means the set has some redundancy, because at least one fellow which can be expressed by the others as a linear combination is a redundant one, right. This is called linear dependent set. We always look forward to linear independence. Okay. Anyway, you can easily see that if a set is linearly independent, then any subset of that set, say S, is also linearly independent. That is because if it is not so, that is, if the subset is still linearly dependent, that means within the subset there is one vector at least which can be expressed as a linear combination of the remaining ones, which means a vector of or a random variable of the set S is expressible as a linear combination of some other members of the set, which makes it linearly dependent. So, I repeat again, given a linearly independent set S of n entries, n random variables x1, x2 dot 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 xn, okay, any subset of that also is linearly independent. However, this cannot be said about sets which are linearly dependent. For instance, set S can be a linearly dependent set, but I can find out a subset which is linearly independent. For example, maybe x1 can be written as a linear combination of the rest, but no other member from x2 to xn can be written as a linear combination of the other ones. In such a case, if I take a subset of S by excluding x1 from S, then that set, that subset, you can call it S prime, is obviously linearly independent. So, I repeat, any subset of a linearly independent set is still a linearly independent set, but any subset of a linearly dependent set may be dependent, may be independent. Why we are so bothered about linear independence and all? Okay. Before that, we just say how to test mathematically whether the given variables form a linearly independent set or not. So, testing, that is, we are testing whether S is a testing whether S is a linearly independent set or not. Okay. How to test? You form a linear combination like this, C1 x1 plus C2 x2 plus dot 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 Cn xn equated to 0. What is 0? Here is not scalar 0, it is not arithmetic 0, it is a vector 0, means it is a 0 random variable, because you see on the left hand side I am combining random variables. What is, so we are given x1, what is C1 x1? C1 x1 is also a random variable which takes values randomly like x1, but in each experiment on x1, whatever value I have for x1, that I have to multiply by a scalar C1, that will be the corresponding value for the random variable C1 x1. Same for C2 x2 dot dot dot. So, and then if we add several random variables like this, we still get a random variable, right? And if I equate it to something else on the right hand side, that cannot be scalar, that cannot be real, that cannot be just a number. It is a random quantity again. So, it is, though I write 0 here, actually mean a 0 random variable, which means a random variable which in each experiment takes a value 0 only. And we say in using probabilistic terms that it is a random variable which always takes, the value 0 with probability 1. Okay. In this case, suppose we form a combination like this, and then we try to find out what are the possible solutions for C1, C2 up to Cn, so that the equality is satisfied. Now, obviously, one solution is obvious, C1 equal to 0, C2 equal to 0, dot dot dot, Cn equal to 0. Then again this equality is satisfied, obviously, because 0 x1, scalar 0 times the random variable x1 means a 0 random variable, because the product will always take 0 value in each experiment. Same here for C2 x2 dot dot dot, same for Cn xn. And when several 0 random variables are added, you still get a 0 random variable, which means the equality is satisfied. Okay. But is there any other solution where at least one or more of the coefficients C1 to Cn are non-zero? Okay. Suppose it is not. I first make a claim and then I just verify it. Suppose the only if only possibility is then S is linearly independent. That is my claim. Otherwise, S linearly dependent. Now, first I consider this, that if there is some other combinations of C1, C2 up to Cn where not all the coefficients are 0, then I will say that the set becomes linearly dependent. And if no such thing exists, then obviously I will show that the set cannot be linearly dependent. And if a set cannot be linearly dependent, it has to be independent. So, there is no other possibility, which means if you cannot express any of the element as a linear combination of the rest, that means effectively that the set is linearly independent. Okay. So, suppose just to verify this claim or this statement, suppose first, suppose only C1 equal to not equal to 0 and C2 equal to C3 equal to dot dot dot, say Cn equal to 0. What does it mean? This means C1 x1 is 0 vector, and since C1 is non-zero, x1 has to be the 0 vector. This is a 0 vector, that is 0 random variable. So, that means set S contains one variable which is a 0 random variable, which is x1. But then that means I can always write x1 which is 0 random variable as nothing but 0 times x2 plus scalar 0, these are all scalar 0 times x3 plus dot 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 0 times xn. These zeros are scalar zeros, not random, not 0 variable, not 0 random variable. But nevertheless, 0 scalar 0 times random variable x2 produces with 0 random variable. Same here, same to other terms, and when they are added, when the 0 random variables are added, you get 0 random variable. Okay. Just to differentiate between scalar 0 and random variable 0, I put an underline between this. Okay. so that you understand now which one is the random variable 0 and which one is the scalar 0. So, that means, if we have got a 0 random variable, it is always expressible as a linear combination of any other set of random variables. So, if a set S contains a 0 random variable x 1, okay, or any element being 0 random variable, it is a linearly dependent set, not independent, because that particular element can be written in terms of the rest. So, it is a redundancy. So, I first started with only one coefficient non-zero, others 0. Now, you go for say 2 coefficients non-zero and others 0. Next, suppose C1 not equal to 0, C2 not equal to 0, but C3, C4 dot up to Cn is equal to 0. This means C1 x1 is C2 x2, which means x1 is minus C1 x1 plus C2 x2 equal to 0. So, it means x1 is nothing but minus C2 by C1 x1. So, x1 x2. So, which means x1 is can be written as a linear in terms of the other random variable, another random variable x2. It is also a linear combination, but having only one element x2 multiplied by some scalar number. So, again the set becomes linearly dependent, because one member can be, at least one member is expressible as a linear combination of another member. Okay, it is a linear combination, but only one entry is there, no other entry to combine, but nevertheless redundancy is still there. And now, you can see that if more and more coefficients are non-zero, you get linear relations involving more and more random variables, okay, meaning that there is redundancy, that is one random variable can be expressed in terms of the rest and so on and so forth. So, it becomes dependent. Okay. So, which means if the set is linearly dependent, then you can get non-zero solutions for C1 to Cn. At least one coefficient is non-zero or more than one coefficient is non-zero. In that case, the set is linearly dependent, or conversely, if the set is given to be dependent, then you must be able to get some non-zero solutions for C1 to Cn, at least for one or more than one of them. Which means, if you cannot get it, if you cannot get non-zero solutions for C1 to Cn, or at least for one of them or more than one of them, that means the set cannot be dependent, which means the set is linearly independent if the only solution is C1 equal to 0, C2 equal to 0, Cn equal to 0. The moment that is violated, a linear relation will emerge. Okay. So, these two terms actually mean the same thing. Dependence means existence of linear relations, which means you get non-zero solutions for C1 to Cn or part of them. Absence of linear dependence means you cannot have such relation, which means in that equation all the values for C1 to Cn have to be 0. Any deviation from that would result in some linear relation between the members or between the random variables, which is a contradiction. Okay. Now, why you are so bothered about this dependence and independence? As I told you, linear independence means absence of redundancy, and dependence means presence of redundancy. And redundancy, whenever there is redundancy, we should, normally we try to avoid, we try to eliminate redundancies. Suppose we consider what is called the vector space spanned by the set S. That means, I consider the set, so I call it vector space V spanned by the set S. What is V? That means, V is set of all possible linear combinations of okay. That is, if you take the elements x1, x2 dot 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 xn, any typical linear combination is what? C1 x1 plus C2 x2 plus dot 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 Cn xn. Now you can take, you have infinite choice for C1, infinite choice for C2 dot 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 infinite choice for Cn. So basically you can look for infinite ways of linearly combining them, but if you collect all such infinite varieties of linear combinations form a set, that is called a vector space V. There actually, if you take any vector, if you take any two vector, each of them is a linear combination of these entries. So if you add those two vectors, again you get another linear combination of these vectors. Okay. So that vector is said to be closed under vector addition. That is, you take any two vectors of the vector space V, add them, you still remain in V, because V consists of all possible linear combinations of x1 to xn. So any combination of x1 to xn and again another combination of x1 to xn, if they are added, you still get another possible combination of x1 to xn. So you remain in V. It's called, we say that V is closed under vector addition. Similarly, V is closed under scalar multiplication. That is, if you take any particular vector of V, which is some linear combination of x1 to xn, say call it C1 x1 plus C2 x2 plus dot 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 Cn xn. Okay, take that, multiply by any scalar constant k, you get a term like kc1 times x1 plus kc2 times x2 plus dot 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 plus kcn times xn. Now this linear combination is, this is again another linear combination, going to V. And another linear combination, and since V consists of all possible linear combinations, we say that V is, this will be belonging to V only, and we say that V is closed under scalar multiplication. Okay. Likewise, you can have the 0 vector, just multiply the elements x1 to xn by scalar zeros, add them, you get the 0 random variable, okay, which is the 0 element or 0 vector for the vector space V. So V consists of the 0 vector also. Okay. Then given any particular vector, you can find its negative. What is the typical vector of V? C1 x1 plus C2 x2 plus dot 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 plus Cn xn. Okay. What is the negative of that? Wherever you have C1, take it minus C1. Wherever you have C2, take it minus C2, and like that. So it's again another linear combination. Coefficients are just reversing their sign, but since V consists of all possible linear combinations, this one also is a member of V. Okay. So negative of each vector remains in V, and likewise. Now that means any element x, element of V, can be written as C1 case A, set S, which is nothing but x1 to xn, given to be linearly independent. Then my claim is, given a vector x, you express it first in terms of x1 to xn as a linear combination, but these coefficients C1, C2 to Cn, they are unique. Okay. That is, given x, the combiner coefficients unique. How do you say so? Okay. Suppose it is not. So I should get x equal to first C1 x1 plus C2 x2 plus dot dot plus Cn xn, and also suppose same x can be expressed as d1 x1 plus d2 x2 plus dot 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 plus dn xn, where d1 to dn, they are not all same of C1 to Cn, at least in one coefficient they should differ. Okay. And left hand side is still x. Suppose this is the situation, our question is, can it occur? Our answer will be that it cannot occur. So the coefficients C1, C2 up to Cn are unique. How? Okay, subtract left hand side from left hand side and therefore right hand side from right hand side. What you get is C1 d1 minus d1 x1 plus dot 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 plus Cn minus dn xn is equal to 0. So, you got another linear combination with new coefficients C1 minus D1, C2 minus D2 up to Cn minus Dn, and not all coefficients are 0, because I mean at least in some coefficients the C's and D's will differ. So, on the left hand side you have got this, and this is equal to 0, but if x1 up to xn this set is linearly independent, then the only way such equality will be satisfied is by making C1 minus D1 equal to 0, which is C1 equal to D1, C2 minus D2 equal to 0, which means C2 equal to D2, Cn minus Dn equal to 0, which means Cn equal to Dn. This is because the set is given to be linearly independent. So, we get C1 equal to D1 dot Cn equal to Dn. So, the coefficients are unique. You cannot have two sets of coefficients which can be used to linearly combine x1 to xn producing the same vector x. Okay, so, uniqueness of the combiner coefficients. So, vector x can be just described in terms of the coefficients C1 to Cn, provided x1 to xn they are fixed choice. So, each vector x has its own unique representation in terms of the coefficients C1, C2 up to Cn. On the other hand, case B, is linearly dependent. Now, we are already giving this, suppose C1 x1 plus C2 x2 plus dot Cn xn, there is given any x, you already have such combination Cn xn, but now additionally you are given the fact that S is a linearly dependent set, which means you can find if you some coefficients D1, D2 like that, Dn xn and equate to 0, where all the coefficients D1 to Dn they are not 0, because it is a linearly dependent set. So, some coefficients at least one or more than one will be non-zero. So, that I write that equation here as a second equation. Now, add left hand side with left hand side, you get that x, and here you get C1 plus D1 x1 plus dot Cn plus Dn xn. And since at least one coefficient or more than one coefficients are non-zero for these, okay, you get another linear combination expression for x, for the coefficients are neither C1 not D1, neither C2 not D2, but something else, which means there are many possible linear combination type expressions for x. So, the coefficients are not unique. That shows the redundancy. Okay. So, that is why we always look for linearly independent set. Now, why this is important for us is this: if the set is linearly independent, you remember we have got such things C1 x1 plus dot Cn xn equal to 0 implies C1 equal to C2 equal to dot Cn equal to 0. Under such case, the correlation matrix of the vector x, that is if R is Ex x Hermitian, where x is this will be positive definite. Now, positive definite means it must be Hermitian matrix, that is easily seen, and we have seen it last time. If you take the Hermitian transpose of R, you have to take the Hermitian transpose of this vector x h. Okay. So, first will be x h and is Hermitian as the first entry, which is x, and second entry will be x Hermitian. So, you get back again x Hermitian expected value, which is R. So, R equal to R h seen already. And now, we say that R is positive definite. Positive definite means for any non-zero vector say A, when I say non-zero vector, I mean it is such a vector where at least one entry is non-zero, if not more. It is not a vector of all scalar zeros. So, if you take like this, and these are complex numbers in general, okay. we should have AH R A, it should be real and positive number. Okay. And that is satisfied. How? It's because what is if it is positive definite, then for any non-zero A, AHRA is a real positive scalar. Okay. It's a scalar number, you can see RA is a vector, column vector, AH is a row vector times a column vector is a scalar number, but it will be a real number also and it will be positive if R is positive definite, that is easily seen. You can write AHE A, which means you can push the A vectors inside the expectation operation, because after all A vectors are just non-random deterministic vectors, which means AHX. I think we did it last time, but today I am doing it elaborately because this is very conceptual, and there is nothing wrong in repeating this. Which is nothing but E of, see, this quantity is nothing but AHX Hermitian, and remember AHX is a scalar number. This row vector is AHX is a column vector, row times column is a scalar number, its conjugate is not, its Hermitian transpose is nothing but just conjugate, okay, just conjugate. Okay. So, I have got a scalar number multiplied by its conjugate. So, it is nothing but expected value of the mod square which is nothing but okay. And this is nothing but, if you call it a random variable, say V, it is nothing but E expected value of mod V square, which is nothing but the variance, okay, of the random variable V. It is not variance, okay, but it is expected value of mod V square, which is always greater than or equal to 0. If it is variance, I have to subtract the mean. So, I am not calling it variance, but expected value of mod V square. Now, this is always greater than or equal to 0, because after all, this mod V square cannot be negative. This is square term, mod V is real and square. It is 0, it is greater than or equal to 0, all right, but when is it 0? It is 0 if V turns out to be a 0 random variable, that is, it's in all experiments it always takes 0 values. So, expected value also 0 value. But question is, can it be a 0 random variable, given that x1 to xn are linearly independent and a1, a2 up to an, they form a non-zero set of coefficients? Answer is no, because if it is linearly independent, the only way this linear combination a1 x1 plus a2 x2 plus dot dot an xn, which is equal to v, the only way it can be made equal to 0 is by choosing a1 equal to 0, a2 equal to 0 up to n equal to 0. But we are choosing a non-zero form of non-zero values for a1 up to an, at least for some of them, which means v cannot be a 0 vector, that is v is a cannot be a 0 random variable, okay, which means E of mod v square is greater than 0. Obviously, real part is easily seen, expected value of mod square, mod v square. So, mod square make it real. So, AHRA, that is a real number you have seen. Now, you see that if the set of random variables x1 to xn are linearly independent, then it is a R is a positive definite matrix, because A Hermitian R A is greater than 0, where A is a non-zero vector. Okay. Some more properties of R. One is the determinant. If delta n is a determinant of the n cross n correlation matrix R, then number 1, delta n is real and delta n is greater than equal to 0, if x1 to xn are linearly dependent. How to show that? First, we know that R is same as R H, because correlation matrix is Hermitian. And what is Hermitian transformation? That is R, you take the transpose and then conjugate, okay, which means delta n, which is nothing but determinant of R, is same as determinant of R transpose conjugate. Now, R transpose is a matrix, just ordinary transposition, and then conjugate. You can easily visualize that if you take this matrix R transpose and conjugate all the element and then take the determinant, okay, you will get the same thing if you first take the determinant of R transpose and then conjugate, because after all, what is the determinant? There will be many product terms which are added. So, if you have first conjugation done on each of the terms, okay, in the each of the terms present, and then take then compute the determinant. That is, if you first take, if you are considering the matrix R transpose, if you first conjugate each elements and then take determinant, what will be doing? All the conjugated elements, there will be, there will be product terms involving those terms, okay. There will be product forms of those terms which are added, okay. That will give you the determinant, but that should be same as if you first compute these and then conjugate, because of the fundamental fact that conjugate of a product is same as product of the conjugates. X y multiplied and then, suppose x y multiplied and then conjugated is same as x conjugated y conjugated. That philosophy is used here. I think you can see it. That is, if you consider R transpose to be a matrix, if you take a conjugate of all the elements and then calculate determinant, remember in calculation of determinant you form products. So, there will be products of this form, x star, y star, that kind of form, okay. You form products which are added. I am saying instead of first conjugating, you first take the determinant. So, again the similar product terms will be there, only the conjugate sign will be missing, and then bring in conjugate on each of the product terms and use this fact that, okay, conjugate of a product is nothing but product of individual conjugates. So, if they are conjugated first and then determinant is computed, you will get the same thing if determinant is first computed on R transpose and then conjugated. And here determinant of R transpose is same as determinant of R, because transposition does not change determinant, which is nothing but determinant of R is delta n to delta n star. So, delta n and delta n star are same, which means delta n is a real number. Okay. Next, we show it is not only real, it is greater than or equal to 0. In fact, it is greater than 0 if x1 to xn form a linearly independent set. So, first assume linearly independent. Then we prove that delta n is strictly greater than 0. Then we assume, then we will go for the fact where for the case where this set is a linearly dependent set, okay, and there we will show that delta n can be made equal to 0, can be 0, okay. It is not necessarily strictly greater than 0, it can be 0 also. Sorry, it is delta n actually is 0, okay. When it is linearly dependent, delta n is actually 0. So, determinant is a unique number, okay, given a matrix. Anyway, we prove this by induction. Okay, we prove it by induction. Suppose it is true up to n minus 1th order, that is delta n minus 1 is not only real, it is greater than 0. What is delta n minus 1? It is the correlation, is the determinant of a correlation matrix involving how many terms? N minus 1 terms. And suppose it is true that if you take n minus 1 terms which are linearly independent, okay, say you take any subset of this linearly independent set, say you take from x 2 then x up to x n, okay, form a vector, find its correlation matrix, call it delta, and take the determinant, you can call it delta n minus 1. Since subset of a linearly independent set is also linearly independent, we assume now for our induction that delta n minus 1 in such case will be greater than 0. That is, it is true up to the n minus 1th order case. This is of course always true, for n equal to 1. That is, if you have only one random variable, because what is delta 1 is nothing but R 1 1, which is nothing but expected value of say mod x 1 square, okay, which is always greater than 0 x, because x 1 cannot be a 0 random variable. 0 random variable, presence of any 0 random variable in a set makes the set linearly dependent. So, this is greater than 0. So, this is satisfied up to n equal to 1, that up to first order. Now, suppose this is satisfied, that is determinant is greater than 0, this fact is satisfied up to n minus 1th order. That is, if you take n minus 1 number of random variables, say x 2, x 3 up to x n, find a correlation matrix for the corresponding vector and take the determinant and call it delta n minus 1, then delta n minus 1 is greater than 0. Okay. All right. Suppose it is true, then you have to show that delta n also is greater than 0. Now, suppose we look for a thing like this, R A, we solve an equation like this, where that means this is equal to say 1 0. We are solving suppose an equation like this, set of equations. Okay. Now, we know Cramer's rule. By Cramer's rule, what is A1? A1 will be what? You first take out this first column, replace it by 1 0 0 0, okay, this vector, take the determinant of that. That is, by Cramer rule it will be, sorry, ratio of two determinants. What are they? that okay, first form a matrix where the first column goes, there is 1, first column is replaced by the right hand side vector 1 0 0 and rest of the items are same. So, that means what you have here r 2 2 dot dot r 2 n and then r n 2 dot 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 r n n. Okay. What is this matrix? You can easily see this is the correlation matrix of the random variables x 2, x 3 up to x n, that is n minus 1 random variables. What is the determinant of that matrix? Determinant of this matrix is just 1 times determinant of the submatrix, because other entries are 0. They contribute nothing to the overall determinant. So, determinant of such a matrix is nothing but just determinant of the submatrix, and the submatrix is nothing but correlation matrix of order n minus 1. So, its determinant is called delta n minus 1. So, it will be say delta n minus 1, sorry, and divided by delta n. Okay. This will be a solution, right. Now, first we are dividing. So, we do not know whether delta n is 0 or greater than 0, but suppose it is greater than 0, then only it will be divided like this. Okay. Now, we make use of the fact that the set x 1 to x n is a linearly independent set, which means the correlation matrix R is positive definite. So, on this equation, what I do? I multiply left hand side on both sides by a Hermitian. So, I have a Hermitian or A. Okay. And what do I get? Just think over it. I give you a minute. Think over it. A Hermitian or A. What do we get? A Hermitian is nothing but A vector transposed and conjugated. Okay. If you now multiply right hand side by A Hermitian, what you get is, I mean you get the first entry conjugated A 1 star. Okay. But A 1 we have already seen is a real number, because determinant of correlation matrices is real, we have already seen. So, A 1 star is equivalent to A 1. Okay. So, n is a real number, but we know that R is positive definite matrix. Okay. R is a positive definite matrix. Okay. That means this is greater than 0. And if it is greater than 0, and we know delta n minus 1 by your assumption is greater than 0. So, the only way we are saying A 1 greater than 0, right, from here, and delta n minus 1 by your assumption is greater than 0, which means delta n has to be greater than 0. Okay. By the way, I forgot one thing. When I said A Hermitian or A greater than 0, I must ensure that A is a non-zero matrix, non-zero vector. But obviously, if I am solving an equation like this, A cannot be a 0 vector, because the moment A is a 0 vector, R times a 0 vector has to be an all 0 vector. It cannot be 1 and then zeros. Okay. So, if a solution exists, the solution cannot be a 0 vector, but it has to be a non-zero vector. So, this is implicit the solution of the matrix that I am looking, the equation that I am looking for is a non-zero solution. It is a non-zero vector, and for such a non-zero vector, this is greater than 0, but this is equal to A1, and A1 we have already seen is nothing but delta n minus 1 by delta n. Therefore, if A1 is greater than 0, then delta n has to be greater than 0, because delta n minus 1 has been greater than 0. Okay. On the other hand, if this set is given to be linearly dependent, then we can say that we can find out something like this: some A Hermitian x equal to 0. If we solve, we can get non-zero solution for A Hermitian and thus for A. After all, what is A Hermitian x? It is nothing but, what is A Hermitian x? It is nothing but A1 star x1, the first entry, then A2 star x2 plus dot 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 AN star xn. Okay. And if it is equal to 0, since the elements x1, x2 up to xn are linearly dependent, I must be able to get some non-zero solutions for A1 star, A2 star up to AN star, at least one of them or more than one of them. Okay. So, that is why I have got a non-zero solution for this vector A Hermitian, and therefore, it is same for A, because if any coefficient is non-zero, say A1 star is non-zero, then A1 also is non-zero. Okay. So, I can now summarize that since x is given to be, I mean x consists of elements which are linearly dependent, I can find non-zero solutions for A, for AH and therefore for A, so that this equation is satisfied. Okay. Now, I multiply this by xh, which means the 0 random variable is multiplied by xh, and then I take expected value, same here, but since it is 0, I will get a 0 vector, right. I will get a 0 vector, and what I get here? A Hermitian R. A Hermitian comes out, E on XXH will give you R correlation matrix, and that is equal to zero row vector. Okay. Now, if you take the Hermitian transposition of both sides, this actually this vector, right. If you take the Hermitian transposition of both sides, that is, if you now apply Hermitian on this side, what you get? R Hermitian, which is R, and A Hermitian which is A. R A is equal to a vector consisting of zeros. So, that means a equation where R A equal to 0, the equation is of this form: a matrix R times a vector A equal to a 0 vector, and we are guaranteed to have non-zero solutions for A. Then it means determinant of R cannot be non-zero, because if the determinant is non-zero, solution is only solution that is possible is all zero solution, that is A is nothing but a 0 vector. But we have been told, we have earlier stated that there can be non-zero solutions for A because of the fact that the set x1 to xn consists of linearly dependent variables. That means determinant of R is actually 0. Okay. This can be argued in a different way also. Suppose R, we come back to the eigenvector eigenvalue part. Okay. Suppose R has got n distinct You can ask me, I am taking n distinct eigenvalues, what happens if they are not distinct? That part I will not prove. Eigenvalues lambda 1 or lambda n. Now, lambda 1 to lambda n, as we know, they are all real, okay, and if R is positive definite, okay, then each eigenvalue is greater than 0 in magnitude. Okay. All right. Now, and corresponding eigenvectors. Again, vectors I am denoting by an underscore here. So, I have this set R E I is lambda I E I equal to 1 to n. Okay. We have already seen the eigenvectors are, they consist of complex entries, but they are orthogonal to each other. That is, E I Hermitian E j is 0 if I and j are not same. Okay. That we have seen if I not equal to j and equal to can be made 1 if I equal to j. Actually, E I, sorry, I am very sorry. Actually, if I and j are same, then it amounts to just mod of E I square. Okay. So, that will be a real number, may not be 1, but if the real number is k, you take the positive square root of k and divide each entry of E I by square root k, call it E I prime. Then obviously, E I prime will have norm equal to 1. That is, if you have got this equal to, is not 1, but equal to say k, then you take the positive square root of k and define a vector E I prime as E I vector by k square root k. That is, each entry of E I vector is divided by square root k. Then you can easily see that norm square of E I prime is equal to 1, because there will be division of k by k. Okay. So, this is called normalization procedure. So, you can have eigenvalues normalized. They are orthogonal when the two eigenvalues are, when the corresponding eigenvalues are different, but when they are same, when I and j are same, the E I H E I is turned out to be 1. Okay. It can be made to be 1. This is the thing. Then what I do, I write R and then I form a matrix E1, E2, dot 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 En, and what do I get? RE1. So, first column of this matrix, you can call this matrix to be T. So, what is the first column of the matrix? The first eigenvector. What is the second column of the matrix? Second eigenvector, like that. So, what is the product? This matrix R times the matrix T. First column will be RE1, then RE2, then REn. And since E1 to En they are eigenvectors, you will have lambda 1 times E1, lambda 2 times E2, dot dot dot, lambda n times En. Okay. Since time is short, I will be doing it a bit fast. Okay. At this you can see, you can easily write like this. You can verify lambda 1, you can have a diagonal matrix, and remember it is a diagonal matrix with real valued diagonal entries, and diagonal entries can be positive if R is given to be positive definite. These times you can call it D matrix times the eigenvectors E1 to En. You can easily verify. see the first row of this lambda 1 and all zeros, you multiply, sorry, is the other way. That is E1 this way, which is nothing but the T matrix. Okay. You can easily verify, because you just, I mean, this is task for you, because today time is short, so I cannot get into these elementary things. Okay. So, in short, you can say R T is T D. So, if I now do this R T T Hermitian, then I get T D T Hermitian, right. I am post multiplying R T by T Hermitian. So, here also on the right hand side I bring in T Hermitian. Now, what is T T Hermitian? That is very interesting to see, and that is what we will conclude with. But before that, what is T Hermitian T? T consisted of first column of T was eigenvector E1. On Hermitian transposition, that first column will become first row. Okay, so you will have E1H with conjugation, column vector becoming row vector. So there is transposition and each element conjugated. So together Hermitian transposition to E1H. Then second column becomes second row. So if E2 was a column vector, now it becomes E2H row vector and elements conjugated, and then ENH. If you multiply this with T, so E1, En, you can see first row times first column, that will give a mod E1 square, which is equal to 1, but E1H times E2 will be 0, E1H times E3 will be 0, E1H times En will be 0. Similarly, E2H times E1 is 0, only E2H times second column E2 will be 1, and likewise. So, this will become identity matrix. So, TH, this means TH is nothing but T inverse, okay, which means TTH is also I. So, TTH is I here, which means R is nothing but TDTH. Okay. So, I am just concluding immediately. So, what is determinant of R? It is nothing but determinant of T, determinant of TH, that is determinant of T times determinant of D times determinant of TH, which is nothing but T inverse. And these two cancels, determinant of T inverse, they cancel. So, you get back determinant of D. And what is determinant of D? It is the product of eigenvalues lambda 1, lambda 2, dot 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 lambda n. As we have seen, if the eigenvalues are firstly real, so determinant of R is always real, that is done, and if they are all positive, if the eigen matrix is positive definite, then each is positive, so determinant is positive. Okay. So, that is all for today. We continue from here in the next class. Thank you very much.